Dear students, today I want to discuss the topic the electric field and charges. Students, keep in mind in our NEET or KEAM entrance examination, we can wait minimum 4-5 questions from electrostatics. For JEE Main, 2 questions. So carefully attend this video, it will help you very much. So at first we can just think about the preliminary aspects of electric charge. You know, are of 2 types. The positive charge means the deficiency of electrons. The negative charge means excess of electrons. And that charges are expressed in coulomb or ampere second and with the dimension as 80. And keep in mind, we can relate with the CGS units, the electrostatic unit or static coulomb and the electromagnetic unit or absolute coulomb. We can relate as 1 coulomb equal to 3 into 10 raised to 9 static coulomb equal to 1 by 10 static absolute coulomb, and is treated as a scalar quantity. And keep in mind that some important properties of charges are transferable from one body to another. And keep in mind, it is quantized in structure, meaning at a particular body, the total charge is an integral multiple of the basic unit of charge, the charge of electron, with a value of 1.6 into 10 raised to minus 19 coulomb. And keep in mind that a transfer of charges is associated with the mass. The positive charge means here the mass decreases. The negative charge means there is an increase in mass. How much? So that is nothing but the number of charges transferred into the mass of one electron. And keep in mind the charge is conserved. There are 3 methods are there for charging a body. The first one through the friction. By rubbing one body with another, the electrons may transfer from the loosely bounded one to the other body. So if you just take 2 objects, the glass rod and the silk cloth, we rubbed it together, the glass rod will lose its electrons and gains the positive charge, and the silk one got the negative charge. It is a very important one. Look the other examples too. The conduction. And keep in mind, in this case, the parent charge is in link with the connection, in contact with that uncharged, the neutral body. And keep in mind, the charged body loses some of its charge and is equal to the charge gained by the uncharged body. The very important, the special method through induction. And keep in mind, the induced amount of charge takes the value as Q dash is equal to minus Q into 1 minus 1 by K. And that induced charge takes the opposite nature, and it depends upon the material under consideration, where K is the dielectric constant or the relative permittivity. And keep in mind, the induction takes place only in bodies, not in particles. Inducing body neither gains nor loses charge. The nature of induced charge is always opposite to that of inducing charge. It is a very important concept. The Coulomb's law, it reveals the magnitude of electrostatic force of attraction or repulsion between the 2 charges, 2 point charges separated by distance r apart. And keep in mind that force are directly proportional to the product of the charges and inversely proportional to the square of separation. And that proportionality constant is a medium dependable one. It is given as 1 by 4 pi epsilon 0. For air or vacuum, that epsilon 0 is called the permittivity of the free space with a value of 8.85 into 10 raised to minus 12 SI unit. In a medium, it takes the value as 1 by 4 pi epsilon Q1 Q2 by R square. And keep in mind the relative permittivity, the comparison of that permittivity of the mediums in air, in a medium by in air, and is a dimensionless, unitless constant. And keep in mind, we have to take as 1 by 4 pi epsilon 0 with a value of 9 into 10 raised to 9. And we can just divide the two, the F medium, take the value as F air by epsilon R. Look, the very important concept, the force between the two charges is separated by a distance r0 in vacuum or air. It is the same as the force between the same charges separated by a distance r in a medium. So we can just write by using the denominator concept as a kr square, take the value as r0 square, then we can relate as r, take the value as r0 by root k. Look, the Coulomb's law in vector form. The force on 2 due to the 1 are expressed as F21. So it repelled by the same nature of Q1, and hence we have to take that vector concept R21. So F21 take the value as 1 by 4 pi epsilon 0 Q1 Q2 by R21 square into R21 cap. So we can write as F21 vector is equal to the minus F12. It is a very important concept. They are equal but opposite. In terms of position vector, suppose the Q1 with a position R1 and Q2 with the position R2, then we can write F21 equal to 1 by 4 pi epsilon 0 Q1 Q2 by R2 minus R1 the whole cube into R2 minus R1. The principle of superposition. And keep in mind, in order to find the force on one due to all others are easily find out by taking the vector sum of individual contributions. It is a very important concept. Look, some examples. For the system shown in figure, find the capital Q for which the resultant force on Q is 0. So here the four charges as a small q, small q, capital Q are labeled as 1, 2, 3, 4. The resultant force on the small q should be equal to 0. Vectorically we can write the force on 1 due to 2 plus the force on 1 due to 3 plus the force on 1 due to 4 equal to 0. So just think about the contribution, the force on 1 due to 2 and is repelled, the force on 1 due to 4. These two contributions are equal but with a 90-degree orientation. So their resultant we can easily find out as root 2 into individual contribution, that is k into small q, capital Q by a square. But there is another contribution, the force on that 1 due to 3. It is acting diagonally and hence its contribution we can write as a kq square by the diagonal as a root 2a square. From that you can easily find the value for q. A good question. The 5-point charges, each of value plus q, are placed on 5 vertices of a regular hexagon of side capital L. Then what is the magnitude of the force on a point charge of value minus q placed at the center of the hexagon? But keep in mind here, only the 5 charges are distributed and one is vacant. On that vertex, if there is another q, then we can easily say the net value becomes 0. That means we can write the f due to a plus f due to all others should, if we take the resultant of them, it becomes 0. That means we can easily write that f2 equal to minus f1, and hence that is nothing but equal to due to a single charge, and hence it is 1 by 4 pi epsilon 0 q square by L square. A good question. Another one, a particle of mass small m carrying a charge minus q1 is moving around a fixed charge plus q2 along a circular path of radius r. Find the time period of revolution of charge q1. And here two oppositely in nature in a circular motion, so there should be a centripetal force. It is given by the electrostatic force of attraction between the charges So we can write as m into v square by r equal to k into q1 q2 by r square, and hence we can easily find the velocity, take the value equal to root of k q1 q2 by mr, and the time period, take the value equal to 2 pi r by v. The 2 pi r is nothing but the total distance, the circumference by the speed v. You get the answer. Two identical balls, each of having density rho, are suspended from a common point by two insulating strings of equal length. Both the balls have equal mass and charge. In equilibrium, each string makes an angle theta with the vertical. Now both the balls are immersed in a liquid. As a result, the angle theta does not change. The density of the liquid is sigma. Then find the dielectric constant of the liquid. And here we can just think about the preliminary aspects. Because of the repulsion, that two balls are with an angle of displacement 2 theta. But you can just think about the one ball, the weight W, the forces acting on it are, the weight W is acting vertically downward, the repulsive force F is acting in that way, the tension is acting along the string. We can split that tension into two components, and this angle theta, and hence this becomes theta. So this component becomes T cos theta, and this component becomes T sin theta. So and equilibrium, we can write as a T cos theta, take the value as the weight mg, and T sin theta, take the value as f. So you just dividing, we get the value mg tan theta equal to f. We can replace that m become the volume into density of the body. But inside the liquid, keep in mind there is an additional force of upthrust is acting. From Archimedes principle, we can write the volume into the fluid density into g, and hence the resultant force become that weight, actual weight minus that upthrust into tan theta. So if you just divide the two, you get the concept. While considering extended objects, you should go with the three important terms: the linear charge density, the surface charge density, and volume charge density. If we are with the charged straight wire, you have to think the linear density as the charge division by length. For a plain sheet of charge, sigma, or the superficial charge density, meaning the charge by area. But for a sphere of or a cube-like object, that volume charge density is charge by volume. See some very important concept, problematic situation. A point charge Q is situated at a distance r from one end of a thin conducting rod of length capital L, having a charge capital Q uniformly distributed along its length. Then find the magnitude of electric force between the two. So here an extended rod having length L, and the point P is at a separation small r from one of the end. Then we know the Coulomb's laws are applicable only for point charges, and hence we can just consider a small element with a charge dq are at a separation x from that point P. Then the force on the charge at P due to this dq contribution we can write as 1 by 4 pi epsilon 0 q dq by x square. So here the variable is x square, so we have to convert that dq in terms of dx. So for that, by using the linear charge density, we can write q by capital L equal to dq by dx. So we can write dq as q by capital L into dx. Then you can substitute here, then you get the value. Then you can find the total contribution by integrating between the limit from r to r plus L. Then you get the answer. It's a good concept. Now the electric field, the space around a charge, its effect can be felt. It can be measured by the field, by the intensity of field. To find at a particular point, we have to place the test charge there. Then the force per unit charge, that is called the electric field intensity, and is treated as the vector quantity, and got the same direction as that of the force. And keep in mind the electric field due to a point charge take the value as 1 by 4 pi epsilon 0 the capital Q by R square into R cap. See the electric lines of force, the very important concept. The tangent at any point gives the direction of electric field. The lines of force do not intersect. If intersect means at that particular R with two directions are possible, but it is not possible. The lines of force tend to contract longitudinally and expand laterally. Look, the electric field lines for some configurations. For a plus Q charge it is radially outward, minus Q it is radially inward, but a plus Q minus Q dipole, look the configuration. For equal charges, for a line of charge it is coming outward the electric lines, but keep in mind for a conductor that lines of force are always normal. And keep in mind the field lines do not exist inside a conductor. Reason the charges are resides on its surface only. Look the figure of uniform electric field, equidistant parallel, then others are non-uniform. And keep in mind the number of lines originating or terminating on a charge is proportional to the magnitude of charge. So Q is proportional to the number of lines of force. The density of field lines is proportional to the strength of the field. It is a very important concept. Here we can say the strength is greater compared to the other point. It is a very important concept. Look, the two important contribution. A ring at a particular point along the axial line. What is the contribution? It's a very important concept. As 1 by 4 pi epsilon 0 capital Qx by R square plus h square the whole raised to 3 by t. And keep in mind at the center x is equal to 0, EP equal to 0. See another contribution, a segment with a linear density lambda. What is the electric field at the center if that arc makes an angle alpha with respect to center? With the simple formula 2k lambda by r sin alpha by 2. Where lambda the linear density as a k 1 by 4 pi epsilon 0. We can move with some problematic situations. A point charge of 0.009 microcoulomb is placed at the origin. Then calculate the electric field due to this point charge at the point root 2 root 70. Then here the position vector take the value as root 2i plus root 7j. Then you know the electric field take the value as 1 by 4 pi epsilon 0 cube by r cube into vector r or q by r square into r cap. But here is vector r, so you just multiply it. Then r cube is what? Just take that magnitude of that r as a root of root 2 square plus root 7 square. You get the value as what? 2 plus 7 as a 9. So that is a very important one. So root 9 become 3, so 3 cube. So you get the answer like this one. Calculate the field at origin due to the infinite number of charges are there. So here Q minus Q, Q minus Q, alternate negative charges are at a separation 1, 2, 4, 8, 16 like that. So that is a very important one. So we have to take the equal same quantities outside kq into 1 minus 1 by 2 square plus 1 by 4 square minus etc. So it is a recurring term of minus 1 by 4. So you get the answer. A good concept, keep in mind. So here we take it as a geometrical progression. The sum as 1 by 1 minus the recurring term. So here the 2 point charges minus q and plus q by 2 are situated at the origin and at the point A00 respectively. the point along the x-axis where the electric field vanishes is. So here the two charges minus q and plus q by 2. If you look at a particular point in between minus q and plus q by 2, the minus q will repel the test charge at that point, but plus q will attract, so there is no zero value there. So we have to find another point here. So it takes the value at its separation x from that minus q, and hence it should be with the separation of x minus a from q by 2. So we have to take, say, the point at here. Then suppose the field vanishes there, the net value should be equal and opposite. So we can write the contribution of minus q as kq by x square, the contribution of q by 2 as k into q by 2 by the separation square. So you get the answer. We are waiting a good question. The field lines for the point charges are shown in figure. That determine qa by qb. If qa and qb are separated by a distance 10 into root 2 minus 1 centimeter, find the position of neutral point. And already said one point, the charge is proportional to the number of lines of force. So just count the number of lines starting from A and ending on B. Starting here, it is a plus charge minus ending. So qa by qb. From A it is 12, from B towards it with 6. So 12 by 6 is equal to 2. Then to find the neutral point, here also the situation is there like before. And hence you have to take an additional point on outside. So from A it is represented as L plus X, and from this one, so from B it is X, and hence we can say from A as L plus X. So then you can easily substitute the values, you get the answer. Look, the motion of charged particle in an electric field. The two situations are there. It moves under a straight line path and a parabolic path. The straight line path when the charged particle is initially at rest. And keep in mind, by using the Newton's second law, m into a is equal to qe by qe, and from that you can find easily the acceleration. How we can find the velocity? V equal to u plus at. The initial velocity is 0, and hence the velocity after a time t is qe by m into t. From that you can easily find the momentum and the kinetic energy by using the basic equations. Look, the next case. When the charged particle enter perpendicular to that with the velocity v, then that situation are treated as like a horizontal projection, and its initial horizontal velocity only, its vertical component becomes 0. Because of the attraction of a negative plate, it will move as a horizontal projection. So horizontally we can give the equation as u plus ad. So the horizontal displacement s is equal to ut plus half at square. So their acceleration, there is no acceleration horizontally, so we can write as x is equal to ut. But for the vertical displacement, the initial velocity vertical is 0 here, and hence we can write as a half into a into t square. So a is qe by m into t square. So from this relation, if we substitute for t as equal to x by u, we can find as y proportional to x square. We can say the trajectory is a parabola. Look, the horizontal velocity at any point, it is a constant, and the vertical velocity as a qe by m into t. Then we can find easily the speed at any point as a root of vx square plus vy square. The electric dipole, it's a very important. The two equal but opposite charges separated by a vector distance, and its direction is always from minus charge to plus charge or coulomb meter, and it is expressed or in another unit as dB. We just discussed the behavior of an electric dipole when it is placed in a uniform field. We can just discuss the three important points. One, the torque acting on it. If theta is the angle between the dipole moment and the electric field, we can say the torque acting on it as P sin theta or P cross E. The next concept, what is the work done to tilt it from an angle theta 1 to theta 2? The work done is given as P into cos theta 1 minus cos theta 2. See the next concept, the potential energy. It is nothing but the work done to tilt it from an angle of 90 degree to any angle theta, that is stored as the potential energy. Take the value as minus P cos theta or minus P dot E. Keep in mind the situations when we can say a dipole is under stable equilibrium and unstable equilibrium. When theta equal to 0, we can say it is under stable, and theta equal to 180 as unstable. Here, in a dipole, we have to find the electric field at an axial point and equatorial point especially. At any equatorial point, its contribution got the same direction as that of the electric field, with a value we can say as 1 by 4 pi epsilon 0 2 pr by r square minus l square the whole square. For a short dipole, we can say it is proportional to 1 by r cube. But for an equatorial point, keep in mind its contribution makes an angle 180 degree with respect to the dipole moment, and its value as 1 by 4 pi epsilon 0 p by r square plus l square the whole raised to 3 by 2. For a short dipole, we can say again it is become half the value as that of the axial contribution as a k into p by r cube. For a short dipole at any angle theta at a separation r, we can find the contribution as 1 by 4 pi epsilon 0 p by r cube into root of 1 plus 3 cos square theta. And keep in mind its net value makes an angle alpha with respect to that line r, then tan alpha we can set it to be equal to half tan theta. Look, some problematic situations. 3 charges plus 2q minus q are placed at the corners A, B, C of an equilateral triangle of side A. The dipole moment of the combination. So, the dipole means two equal but opposite contribution. Therefore, we can split that plus 2q into 2 plus q plus q. So, this plus q makes a dipole with a minus q. So, the dipole moment takes this direction. Both are makes an angle of 60 degree between them, and hence the resultant we can easily find as root of p1 square plus p2 square plus 2p square cos theta. But in short, we can use 2p cos theta by 2. You get the answer. Look the another concept. The electric field due to an electric dipole at a distance r from its center in axial position is capital E. If the dipole is rotated through an angle of 90 degree about its perpendicular, the electric field at the same point will be. And keep in mind here, because of the tilting, that point under observation become the equatorial point. Hence, the electric field become half. We can wait one question from this term, electric flux. It is a very important concept. And keep in mind the lines of force coming normal to a surface are called electric flux. In integration, we can write as integral E dot dA or E dot A, EA cos theta, where theta is the angle between the electric field and the area. And here, a cylinder is placed in an uniform electric field capital E. You just look the 3 contributions, and here that area vector makes an angle of 180 degree with the electric field direction, and there theta become 180, and hence the flux become negative. But here the flux become positive, but here becomes 0. And hence we can say the very important concept that entering lines of force are taken as negative and the leaving lines of force are taken as positive. The very important concept of the Gauss's law. In order to find the electric field due to different configurations, we can use this concept. The surface integral of E dot dA take the value of 1 by epsilon 0 times the charge enclosed. If it is placed in another medium, we can say you have to multiply epsilon r in the denominator. So here, the application of Gauss's law. a straight line conductor, a thin line of charge. We want to find the electric field at a separation r. We can just use the concept as 1 by 4 pi epsilon 0 2 lambda by r. But if it is with a plane sheet with a surface charge density sigma, at a separation it is said to be uniform with the value sigma by 2 epsilon 0. But if it is a conductor, then 2 contributions, so sigma by epsilon 0. Look, the electric field due to a solid or hollow conducting sphere, they are equivalent in the sense here that in both the cases the charges are concentrated or resides on its surface only. We need to find the electric field at outside point at the surface and inside. And keep in mind, at outside point we can consider all the charges are resides at the center. Then we can treat as a point charge, and hence the contribution become k into q by r square. On the surface it become k into q by capital R square. And at any point inside there is no charge enclosed, and hence the electric field contribution becomes 0. So look the graphical representation. Here for a non-conducting sphere, an outside point we can treat as a point charge on its surface also, but the case become entirely when the point is well inside. So there the contribution at a separation small r from the center is 1 by 4 pi epsilon 0 qr by capital R cube. Look the variation. At any point inside till the surface, that electric field proportional to small r. See the flux from the Gauss's law. And keep in mind some problematic situations are there. So here a hemispherical surface, it is placed in a uniform electric field, but we are comfort with one data, the total flux should be equal to 0. Reason, there is no charge enclosed. But it is because of the two contribution, one the entering area, the plane, and the leaving area, the curved one, but should be equal to 0. So we can easily find for that flat surface pi r square into E, but entering minus. So the flux due to the curved one become plus pi r square into E. See the case here, this is the entering, this is the leaving. So the total flux becomes 0. So the entering we can find easily. So here a sphere, at the center a charge is here. Then what is the contribution due to a half sphere? So here the total value is q by epsilon 0 by 2. The similar concept here. Then how we can find if the charge is placed on off the corner? So you can just draw a Gaussian surface, a symmetrical one, by placing that charge at the center. So it is consists with 8 cubes. So the total value become q by 8 epsilon 0. So we can wait with some good problems. The inward and outward electric flux for a closed surface in units are respectively 8 into 10 raised to 3 and 4 into 10 raised to 3. Then the total charge inside the surface is, already we know that entering flux are negative and the leaving flux are positive. By using the Gauss's theorem, you can find the relation for Q as the total flux into epsilon 0. You get the answer. A good question is waiting. The 3 infinitely long charge sheets are placed as shown in figure. The electric field at the point P. At first go through the figure. Here the 3 plane sheets are there. At a separation minus A from here with a surface at density minus sigma. At a separation A from that center with a surface at density minus 2 sigma. At a separation 3A with a surface at density sigma. We have to find the contribution here at the point P. So we have to place the test charge there. But this surface will repel there, but these two will attract there. So the electric field at the point P got the same direction, that is always away from that along this direction, along the negative direction, and hence we can easily find that value. You know, for a sheet the contribution is sigma by 2 epsilon 0. The second one got the minus 2 sigma, so something like that. So you get the answer. You just add the three contributions. At a point 20 centimeter from the center of a uniformly charged dielectric sphere of radius 10 centimeter, the electric field is 100 volt per meter. The electric field at 3 centimeter from the center of the sphere will be, at any outside point it is a k into q by r square. But at any point inside, the kq division by r cube. And you can just substitute for kq as e out into r square. Then by substituting the values, you get the answer. The students try to solve some outstanding questions from this electrostatic chapter. Reason we can wait the brain questions from this one. So God bless you. Take care. Thank you.